Electricity, capacitance. Questions to ponder. What is capacitance? How much charge does a capacitor hold? How is capacitance determined by a capacitor's structure? What is a dielectric and what does it do? What is the circuit symbol for a capacitor? How much energy is stored on a capacitor? Let's first talk about what capacitance is. Capacitance is basically the energy stored in an electric field between two charged plates or sheets of conductor. If we have this situation where we have a battery, for example, it has a potential difference or a voltage, and we connect that battery to these two plates. That's what they're called in capacitors, these plates of conductor. The positive terminal of the battery will attract the electrons that are in this sheet of conductor, and they'll move toward the battery terminal. Upon those charges moving, as soon as those charges start to move, it creates an electric field that'll draw the negative charge from the negative terminal of the battery here, and we will say that this capacitor, that's what a device is called that has capacitance, this capacitor will charge up, and it'll continue to charge and continue to charge until the charge on this capacitor is great enough that the potential difference between the plates is equal to the potential difference of the source that's creating the charge difference. So once it charges up, in this case to V here, a voltage of V between these plates, then it will stop charging and there will be no more current flowing. At that point, if we open the switch, the charge will be trapped on this capacitor, and there will be energy stored due to the electric field that's being held here because of the difference in charge between the two conducting plates that are in opposition here. In this case, it's two plates, and we have an air gap in between these two plates. So that's what capacitance is. It's charge stored on two plates that are separated from one another, and it's storing energy in an electric field between these plates. Another way to look at capacitance is if we increase the amount of voltage that is, or we increase the amount of potential difference here, we can create greater and greater charge on these two plates, and we get a linear relationship, and the slope of that linear relationship is what we call capacitance. So the charge stored on these plates is equal to the capacitance in this configuration times the potential difference across these plates. And so capacitance is equal to the amount of charge per voltage or potential difference in this configuration. Next, let's take a look at the structure of a capacitor here, and how much capacitance is created based on this structure. It should only make sense that if we have more, if the plates are larger, there's more surface area, that there will be more charges that can be pulled off of the plate, and therefore more charges drawn onto the lower plate. So the greater the surface area, the greater the capacitance. And then it should also make sense that the farther apart they are, the less the electric field strength, and therefore the less the capacitance. So the farther apart they are, the less the capacitance. Or the other way to say it is the closer they are together, the more the capacitance. So surface area and the distance between the plates are the two main players that create capacitance. We also have this term, which is the Greek letter epsilon, epsilon naught, and epsilon naught stands for the is a variable for the permittivity of free space, and basically this is a proportionality constant that makes these two variables, the surface area and the plate separation, create this capacitance. So it's a proportionality constant, 8.85 times 10 to the negative 12 Coulomb squared over Newton's meters squared. And let's talk about what we measure capacitance in, and that's a unit called the Farad. given a symbol capital F, named after Michael Faraday. The next topic, if we have our capacitor here with our two conducting plates, let's talk about what we can put in between these plates, and it's called a dielectric. Before, in our previous example, we had air in between these two plates, but if we put certain materials between these two plates that are insulators, that don't allow current to flow from one plate to the other, but do have certain properties that actually magnify the electric field strength between these two plates. There's a polarization process that happens within this insulated material that actually, again, magnifies and concentrates the electric field and actually increases the capacitance. So dielectrics, the materials here, they have a value called the dielectric constant, and that tells you how many times more they will concentrate the electric field than if it were just in a gap with air between the two plates. Usually we don't have this as an equation. Usually we have this as an equation where we change the permittivity of free space into the permittivity of the dielectric by multiplying the dielectric constant by the permittivity of free space. And this is usually on the order of 4 or 5 or 6, a factor of 4 or 5 or 6 or something like that, times better than the permittivity of free space. So capacitance now really has 3 variables. It has the dielectric variable, the plate area, and also the separation between the plates. One last comment is dielectrics are also useful not just because they can magnify the intensity of the electric field, but also because we can get these plates really, really close to each other. If we have a thin dielectric and we can squeeze these two plates right next to each other with that sandwich of the dielectric, keeping the current from flowing across or charge from flowing across, and also magnifying the electric field. As I mentioned earlier, capacitance is measured in Farads, given the symbol capital F, named after Michael Faraday, shown down here. And 1 farad is equal to 1 coulomb per volt. If you remember, capacitance is equal to the amount of charge per potential difference. So, but a coulomb is a huge amount of charge, if you remember that. So 1 coulomb per volt, this is a small amount of potential difference, is a huge amount of charge for such a small potential. So most capacitors, the devices that have capacitance in the range of microfarads, 1/millionth of a farad, or nanofarads, 1/billionth of a farad. So you'll see microfarads a lot, 1 times 10 to the negative 6 farads, and then nanofarads, which is times 10 to the negative 9 farads. Capacitors. Capacitors are the devices that have capacitance. Here are some capacitors in this particular circuit, and those are called disc capacitors, and that's their circuit symbol. We also have other kinds of canned capacitors here, where the metallic plates are separated by a dielectric, and they're rolled up here to create as much surface area as possible to increase the capacitance. And then we have electrolytic capacitors here that use an oxide layer as their dielectric to have it be super, super thin and create pretty high levels of capacitance for these tiny packages. The problem is they're polarized, and if you put them in the circuit backwards, they pop like a firecracker. The last kind of capacitor here to look at is a variable capacitor. By turning this rotor, the amount of surface area that's overlapping the stator here is either increased or decreased. So if you turn it this way, it increases. If you turn it that way, it decreases, and you can vary the capacitance, and so that is called a variable capacitor. In this case, it's air that is the dielectric, and therefore usually a tiny value of capacitance. But capacitors are used extensively in electronic circuits.
Ready?
Capacitors definitely store energy.
Beautiful, man, beautiful.
Now it's time for you to try a sample problem. So what is a capacitance if a capacitor has plate area of 0.02 meters squared and plate separation of 2 times 10 to the negative fourth meters and a dielectric constant of 8? Remember, that's the capital K. Good luck on this one, and come on back after you've given it a shot. So how did you do here? Well, we have a capacitor that has a dielectric, and so we would use this equation right here because it called out the dielectric constant of 8. So once you're using this equation, and you'll have to also use the permittivity of free space here, it is a simple plug-in problem. So pause the video and check out how you did. All right, we have one last idea here with capacitance for this video, and that is the idea of the energy stored on a capacitor here. To understand the idea of energy stored, before we had the work that was done to move a charge in a uniform electric field would be the potential difference times the amount of charge that was moved. The situation is a little bit different with a capacitor because when you connect this capacitor to a potential difference and it starts to charge, these negatives start to move. Initially there's no potential difference opposing that motion of the charge, and so when the potential difference is small, it's very easy for the charge to move off of these plates. But as the charge starts to move off of the plates, the potential difference starts to increase. The voltage starts to increase across the capacitor here, and therefore it makes it harder to continue to move charges off. So as the voltage gets bigger and bigger here, the charge gets greater and greater, and that's what's causing more and more voltage. So in our equation here, because this voltage starts at 0, or this potential difference starts at 0 and goes up to V, the averaging of that increasing voltage would be 1/2 V, would be the average in this particular case. And so the other way you can think of it is that the work done to charge a capacitor here is equal to the area under this charge versus potential difference plot. So we get 1/2 Q times V, which would be this area, and again it's the averaging of that potential difference as we're charging the capacitor. That's the amount of work done. So work, since potential energy is equal to the amount of work, when we do work to charge a capacitor, if we flip that switch, we would have stored potential energy on this capacitor, and that electrical potential energy stored in the electric field in the capacitor here is what we want to find an equation for. Since Q is also equal to the capacitance times the voltage, we can get everything in terms of capacitance and voltage, or capacitance and potential difference. If we plug CV in for Q here, then the potential energy stored on a capacitor when it's charged to a particular potential difference is equal to 1/2 CV squared. So that's an important equation to know, because that's one thing that capacitors do, is that they store energy. And one more quick sample problem. How much energy is stored on a capacitor with a capacitance of 5 microfarads and 12 volts across it? Give this a go and come on back when you're done. So how did you do? It's basically a plug-in problem here with our potential energy equation for capacitance. So go ahead and pause the video and check out your work and see how you did. Only one last thing to do, and that is to simulate it. So search in your browser for FET Capacitor Lab, go to FET and run the Capacitor Lab simulation and get a real feel for capacitance. So questions to answer. What is capacitance? How much charge does a capacitor hold? How is capacitance determined by a capacitor structure? What is a dielectric and what does it do? What is the circuit symbol for a capacitor? And how much energy is stored on a capacitor? Scratch's parting idea. and good luck with your continuous improvement.